Okay. Hassan, you've raised your hand.
Hello, Mr. Raj. How are you doing? Nice to see you again.
Good to see you. How's it going? I'm fine, thanks.
That's great. Okay, so I was just asking that. So we are all of the candidate is doing his great effort in this project. So I was just asking who is doing a documentation part. I mean to say that the project will be in a documents form, so we can just post it on a GitHub and somewhere, or maybe present it to the Omdena team. So who is doing the documentation part?
No one's actually doing that at the moment, but I think I will. Me and Salman will probably put it all together into one sort of coherent document. We'll probably come up with some sort of presentation as well, and as well as the deployment aspect of it. I think getting everything down to where it needs to be first is probably the most important, and then we'll create some nice documentation around what we've done. What happened over the couple of weeks we were working on the project, highlight a couple of key insights and highlight some good work that people have contributed. And of course that will, as I say, will come with the deployments as well. We'll try and basically we'll record a call where we go through it, and we can use that on, for Omdena. Omdena can repost it, and by all means you can use the documentation, the files in the GitHub as part of your personal project record, so you can add it to your resume and whatnot as well. But I wouldn't worry about the documentation until the end. Me and Salman will put it together over the next week, and if we need to reach out to anyone just to get a bit of clarification on anything, we certainly will do. But yeah, don't worry about that for now.
That will be amazing. It will be amazing.
Cool. Well, thanks everyone for coming. I've over the past couple of weeks, well, first of all, apologies for not having the meeting yesterday. I had a couple of things to attend to, and Salman is obviously traveling today, so won't be doing the Sunday session. But we'll pick that back up next week. That's not a problem. But yeah, over the past couple of weeks, everyone's been enhancing the data sets, creating some notebooks around feature engineering based on a couple of the insights that were found in the EDA process. And I see that a number of people have tried different things. So the effort that everyone's put in has been fantastic so far. We've got some really good insights, and I think the next stage of model development should have a not an easy ride. I don't want to say that, but some good information to go on. From the Slack chats, we've had a couple of people who'd like to share some of the findings that they've had over the past couple of weeks, well, the past week, sorry, during the feature engineering phase. Just out of pure memory, Gordana, would you like to go through what you've found? I believe you wanted to share some of the work you've done.
Hi everyone. Yes, but maybe is it better that we start from some other group?
Yeah. If anyone wants to share anything that they've done, feel free to raise your hand and share your screen. You should be allowed to share your screen. I haven't had a chance to look through every single piece of work, but there has been some good findings. I think where it is. Let me just have a look on the group chat.
Mr. Royce was raised a hand.
Oh yeah, Francesca, sorry. Did you raise your hand?
I was about to share my screen, but if you...
Oh, go on then. Go ahead. Go ahead. I'll turn my camera off.
So this is almost the same notebook that I presented in the previous meeting, but I have made a few changes. So first of all, Let me go through it again so we can have a review. Here I'm just checking for columns that have up to 5% missing values, and then I drop these columns, and then in this second node class there was unclassified, so I replaced them with data missing. And similarly in the junction control feature we had data missing there also, so I also replaced them with data missing. This is a function for comparing the effect of imputation on the columns. So based on this observation, there was a change in before and after the imputation. So I dropped this column, and also in the junction control feature we had a misspelling, so I replaced them with the correct spelling. And yeah, so in the previous session, the notebook I presented, I split the time into hours, and yesterday I split the date column into day and month, and this is how it looks after splitting. So I removed the date column, dropped the date column, and I replaced it with day and month, and year was already present in the data frame. Also, these two columns, like we discussed in the previous meeting, that these are also represented by latitude and longitude, so I dropped them. And yeah, so on the accident severity feature, this is a column transformer. So on accident severity feature, I am applying ordinal encoder with these three categories: slight, serious, and fatal. And on the columns that has more than 5% missing data, I am just applying simple imputer with filling the values with data missing. Um, so this is how it looks like after imputation. And so I tried to include this label encoder inside the column transformer, but it turns out that here that label encoder could not be used inside the pipeline and column transformer due to this issue that label encoder don't follow the standards scikit-learn convention for this. So I had to do it outside the column transformer. So this is the data frame that I came up with after the imputation and encoding, and we tried to train a few models on this, but it did not contain the day and month column at that time, and it had around 85% accuracy and 85% precision, and the best model has these scores, and F1 score was like 78, I guess. So then I wanted to try something out to improve the scores, so I tried to do feature scaling on it, and this is the visual representation of the dataset before and after the scaling. So you can see that after the scaling, all the values on all the columns on the same level, and this is now the dataset after the scaling. So I have not tried to train any models on this data, so we will have to see there. And after introducing the few new features like the day, month, and hour, I wanted to check the correlation between accident severity column with the rest of the column, in hopes of maybe the new columns have created some sort of high correlation, and but turns out that all the columns, none of the columns show a high correlation with the accident severity column. So yeah, right now I'm at this point, so I will try to train to check a few models, training a few models around this data set and see if it improves the results or not. And yeah, that's all.
Yeah, good work. Have you considered? I may have missed it, but have you considered? Our target variable is quite unbalanced. Have you
Yes,
tried
yeah.
to?
Yeah, I noticed this, that it had like only 14,000 values in the fatal category. So I googled about it, and it was talking about stratifying. So I just have to use here the
Yeah, the
stratify.
Stratify. Yeah.
Yeah. So yeah, but yeah, I will try that. Yes, I will try doing that.
Yeah, I mean, there's a number of ways around it. I mean, there's there's oversampling as well and undersampling the majority class. It's just that, if we're in a classification problem, and we've got 85% of our 85% of one of the classes, it accounts for sorry, let me just reword that. I can't even get my words out today. One of the classes represents 85% of the total number of samples we've got. Even if we were, say, even if it's going to get 85% of them correctly, if you know what I'm predict them correctly. So it's not going to be a true reflection of the model performance. So we can't really trust it. I would also be interested in see if you could plot your learning curves as well.
Yes, ROC,
on the models. Yeah,
they are on my like to-do list. I will be doing it.
Yeah, cool. Yeah, but I think that some of the steps that you've taken have been you've taken some of the observations we've had from the EDA and taken them on board and try to build a data set that is suitable to input the model. But yeah, in terms of the classroom balance, that will need to be dealt with. We can, there's other way around it as well, where if I wouldn't suggest this, but if we were in another sort of if it wasn't like sort of fatal, serious and slight, would it be a possibility to combine the serious and the fatal categories together? It's them sort of questions that you could ask and experiment with to try and make up, so you've only got two classes, but even still it might be significantly overbalanced, but that's one way of doing it. So yeah, just try a few experiments with the oversampling the number 2 category, and that should be the fatal, shouldn't it? Should be the fatal. Try and oversample it and try and undersample the majority class and just see what happens and see how it affects the performance. But I don't think you'll be able to get a real grasp on that without using a learning curve, if you know what I mean.
Yeah, I understand what you were saying. So like the accuracy score, and I talked about the accuracy score and the F1 score. So how much would be like what score? How much would be a good score for accuracy? And
well, in this particular test, accuracy isn't really the greatest. I would probably just stick with the F1 score, closer to 1 is better. But again, if your classes are unbalanced, you're not going to get a true reflection of the accuracy.
Yeah,
that's the issue.
90 plus, or 95 plus.
Yeah, well, that's another question. What is good enough? Now we have to assume. Let's imagine that we're doing this in real life, and we've been approached by local authorities. What would be a good enough accuracy to dictate if a particular junction needs improving? Because what we predicted that this particular junction, with the particular information we have, always has serious accidents. Is it going to be 60%? Is it going to be 80%? Or is it going to be is the threshold going to be 95%? The model that we produce in industry, it's a very easy trap to fall in. As a machine learning engineer, you always want the highest performing model. And, you could waste a lot of time gaining 0.5% in model performance. What is important more than that is return on investment and your business metrics. What does the business dictate is important? What's their important metric? What do they want to see? If we don't know, because we're not doing this for anyone in real life, but I would think an accuracy of about 85% would be reasonable to start to say, listen, we can predict with 85%, sort of confidence that this particular junction is causing serious accidents. I think that's enough, but it would entirely depend. But that is quite a significant question you've asked there. What is good enough? When do you call it quits? And it's closely tied to the business metrics. What are you trying to solve? We don't want to waste time and effort incrementing a model performance by 0.5%. You know what I mean? Let's stick with what's important. So in my opinion, 85% would be adequate to because at the end of the day, people's lives are at stake. And if you can easily, with 85% with confidence, you can change something on the road that saves lives. I think that's pretty reasonable. What does everyone else think about that?
I think it's important to understand when we're talking about the percentage, the accuracy, what specific accuracy we're looking to achieve. So I've done a whole bunch of modeling and some comparison on this data already, and due to the class imbalance, even doing some exotic stuff with changing sampling rates and whatnot, the data runs into the fact that comparatively there are so few data points for the fatal accidents, because as it turns out, there actually just aren't a lot of fatal accidents over this period. Like 14,000, it's terrible to say that 14,000 is a small number, but comparatively it is a tiny number.
Absolutely.
And so the issue that you run into is that what we're actually trying to do is we're trying to predict, trying to do the positive predictive value for fatalities, for fatal accidents, which is a different metric than just pure accuracy. You're trying to see when the system is predicting that something is going to be fatal, you want to know how accurate it is at predicting that it's going to be fatal. So when it says something is fatal, you want to know that it's going to be. And unfortunately, at least in my models so far, and I still have time to work on this, I have been unable to get much above 50% accuracy in predicting that a crash will be fatal, or not.
Yeah, I get the point. Maybe in that case we can merge these, like Rich mentioned, we can merge these two, then this will at least balance the data a little bit, if not a lot, and only the serious and fatal accidents.
I mean that is, I think, one way to solve the issue. I mean, I think that there might be some other things that we can kind of also consider during the modeling, discrete portion of this to maybe work around a little bit more.
Yeah, I was working on the feature engineering, and I tried to find some relationship between any of these columns, but to me all these columns are so unique that I cannot find such a relationship in which I can produce a new feature or something like that. So I am having a hard time with that.
Yeah, I would recommend just using maybe a tree model. and use the feature importance method and just see what it says and see if it sort of matches your intuition.
Okay.
That might help.
I'll
But yeah, I
see.
think Michael raises a good point. You know, it's you want to avoid fatal accidents at all costs, and you know, if there's slight incidents, you don't really want to have any accidents at all, but you'd want a higher accuracy on the serious and fatal accidents because they're going to be the ones who have the most casualties, and that's what we're avoiding. We're not really concerned about damage to vehicles or anything. With this, you know, the slight incidents generally are just going to be mostly vehicle damage, a high proportion of them anyway, and the serious and fatal ones, they're going to be the ones which, you know, human life is at risk. So, you know, our predictions are, you know, should be weighted to that sort of end. But as we say, as Michael, you know, pointed out, we've got only a very small sample of fatal accidents. So how are we going to deal with that?
Yeah, it was a very good point by Michael.
Absolutely, yeah.
Yeah. So we first of all, I'm new to I don't have a fair amount of expertise in the modeling phase, but I learn along the way. Yeah. So
of course, yeah. That's the best way to do it. You know, the best way to learn is just to get stuck in. Michael, are you in a position to share any of the experiments that you've run, just so we can get a better idea in the group?
Sure. Yeah, I can throw this up on the screen, and we can walk through a couple of where I've been so far. Hold on 1 second.
We just had a hand raised. Jawaria, is it pronounced? Jawaria Rashid, are you okay to talk? Yeah. Or was it an accident? Yeah, Michael, go ahead, and if there's a question, just pop it into the chat.
Can everyone see the notebook that has been shared now? So this is a continuation of what I last week during the EDA portion, I had kind of shared a bit about like what we were doing in terms of selection and how we were doing some of just the basic like data imputation. We've encoded and gotten I just one hot encoded everything, essentially. Nearly all of the items in this all of the features are categorical, and so they need to be encoded.
Sorry to interrupt, Michael. Could you just zoom in a little bit? Someone's just put in that they're struggling to see. Just zoom in a touch.
Sorry. Hold on. Yep.
Cheers.
Yeah. Is that better?
Is that better, Hassan?
Yeah, it's fine now. It's fine now.
Okay. Sorry.
Cheers.
Yeah. So I one hot encoded everything. I did a category encoding on our slight, serious, and fatal, our target variable, split us up into a training and test set, and then I just ran us through a series of different like just to see what the different classifiers are going to kind of like get us in a ballpark. And then this is the code that does most of the work. It looks at how long it takes to train. Right now I'm using accuracy score. I'm actually retooling this to use precision, which I think is going to be a more accurate metric for what we're actually looking to achieve. Yeah. And then I have it printing out a confusion matrix, which essentially shows us for each of the for the target variable for each of the given categories in the target variable. It shows us what, like, essentially it matches up with was it slight, and false positives, true positives, so forth and so on. And then I have it printing out the positive predictive values for it. So I ran this on two different data. I ran the same set of tests on two different data sets. One of them is just the accident data set, and the other one is the accident data set that has been joined with the vehicle data set, to see if that provided any additional information. For the most part, in an interesting turn of events, decision tree classifier is 75% accurate, but actually returns our best overall. It actually returns fatal values. The problem is that because we have such an imbalance, and I haven't dealt with a lot of in this notebook, I haven't dealt with any of the imbalance problems directly yet. Everything just kind of goes towards just guessing that everything is a slight accident, and just achieves a delightful 86% accuracy for guessing everything is a slight accident, because that is the easiest way for the machine to learn. But one thing that is interesting is that when we add in the vehicular data, so this is the combined this data set was merged on accident index, and it brings in the vehicular data, although I didn't do anything exotic like bring in like multiple vehicles for multiple vehicle accidents. It's just whatever the primary vehicle involved with the first vehicle that was involved in the accident is what's getting picked up at this juncture. When you include that information, it actually improves the overall accuracy of the model, and some of the models further down the light gradient boosting classifier actually is somewhat accurate-ish. It doesn't predict very many things are fatal, but it is pretty accurate when it is saying that something is fatal. So that's kind of where I'm at this juncture. Looking at what this is, I think that some areas where this is like 86.5% is the best accuracy so far. Accuracy, like I said, I don't think is going to be the most useful. I think precision is going to be a better overall score for these. I just have to retool the notebook to deal with that. I think that there needs to be. There needs to be some pruning. I think that I'm going to try and pull out, like Richard mentioned earlier, pulling out feature importance. I'm going to try and pull out some feature importance and see if some of because right now there's just so many. There's just so many features that none of them are sufficiently important to actually provide any, like, individually. They don't provide much in the way of movement in terms of predictive value. So I think pruning that, and then I think dealing with the class imbalance between serious, slight, and fatal will hopefully yield some better results. But that's more or less where I'm at right now.
Yeah, no, that's great work. Have you got any sort of ideas what you're going to try with for the class imbalance? I know a couple of people have mentioned things like smote and whatnot, but is there anything you thought about dealing with directly?
The two things that I have looked at doing are changing to a precision score instead of an accuracy score. Should allow for most of the models, should change the way the models are learning, and I think will be more beneficial than just because with precision, the model is punished more for getting things wrong than it is rewarded for getting something right, if that makes sense.
Yes.
Which is like with an accuracy score, all it cares about is just reaching the best accuracy that it can get, but it's not really punished when it gets something when it like intentionally gets something wrong, if you know what I mean.
Yeah.
So like, because we have such a high imbalance, so precision score is one thing. The other thing was, I think, because we have such a large data set, I do think that some variety of selective sampling from the data set, where as much as we possibly can, we sample all of the information from the fatal accidents, and then sample significantly less of the non-fatal accidents. The reason being is that it will balance out the classes a little bit more, but it shouldn't change, I don't think, significantly its ability to predict slight accidents, because the vast majority of accidents are slight accidents anyway, so it's going to be better at that. So
Yeah.
but I don't have any
absolutely.
I don't have any specific. I haven't. I only just finished where this is like earlier today, so I haven't had a chance to kind of deep dive into where the to go from here. So
Yeah, I think as well. It's not really. I mean, I haven't particularly used it for an unbalanced data set before, but there is a passive aggressive classifier. If you've ever heard of it, it's in scikit-learn, and when you were saying about precision and it punishes misclassifications, the passive aggressive classifier also does that. It basically, punishes the algorithm for getting the wrong category, so it takes into account unbalanced. And apparently, I haven't. That's the thing. I read the material on it, and I've come across it maybe once before, but I've never actually used it. But it sounds like it might be worth giving it a go. I'm not really up to date on the research with it, and I don't know if it's been improved since it was. I think it was first put out 2014, maybe. But it might be worth having a crack at it, a passive aggressive classifier, just see how it runs. Before trying to balance these classes, it might be worth having a go.
absolutely.
Yeah, I'll see if I can find some information about what's been going on with the passive aggressive algorithm. As I say, it's not it's not one that is talked about a lot. It's quite niche, but it might be worth a go. Let's check it out. Okay, well, thanks very much for that, Michael. Great work. And I think, Jawaria, you had some insights. Do you want to share your screen and show us some of the insights that you've managed to draw? If you're still there. No, okay. I'll tell you what. We've got 3 minutes left, so I might as well just restart this meeting, and we'll all join back in again if that's okay. Just refresh, and I'll see you in a couple of minutes. I just want to also bring to your attention Retton's vehicle analysis pipeline. He shared it with the group earlier on. Let me just share my screen, because he's made some fantastic plots. Which screen is it? This one. So he's been imputing some of the features, and what he's done is plotted the distributions and how it's affected the values within the specific feature. And he's created some fantastic graphics to sort of, to understand the intuition behind each sort of imputation and understand which one is more effective. And like the one he's done here for the driver IMD decile, it seems that none of the imputation techniques seem to have done very well. The distribution of the input values are way out of line. and it's the same for the age of vehicle as well. We can see the original data and the effect the imputation has had on that data. So it's a very, very intuitive way to look at the imputation techniques, and it's a great demonstration. So, you know, if this is the case with the mode, the mean, and the median imputation, you know, you could try different strategies then. The KNN neighbors imputation, some of it maybe a like GMB imputation, just to see how it affects. But you know, your sort of standard fit, your go-to methods of imputation don't seem to be working very well. And also these ones as well, you can see the effect on some of the other features. The engine capacity, we can see that the mean imputation is definitely the best result, and it's the same with the engine capacity as well. The mean imputation seems to fit the original sort of distribution the best, even though it's slightly skewed, but the values seem to be around the same sort of variance. So yeah, it's quite a you know, a decent notebook that Retton's put together, and it's definitely worth having a look at it and using some of the ideas in there on you know, some of your experiments and especially in the accident data as well, because it's, you know, it's quite vast kind of thing, and you can actually see how your imputation methods are affecting the distribution, because that is a very important part of it. So yeah, take a look at that. I think that one was just something that I did want to share. Let me just quit that. Okay. Where's my chat? There we go. Yeah, so it's a good way to look at it. Has anyone got anything else they'd like to share with the team that they've been working on over the past week? Yep, Gordana, go ahead. It's all yours. You're on mute as well. Sorry. There we go.
Yeah. Okay. Hi, everyone. Okay. I worked a little bit, but just a little bit on feature engineering regarding in the group for vehicle analysis. And it's not some extra, some very good information. It's not something impressive, but some basic techniques. Just a minute. Can you see my screen?
Yep, we can see it.
Okay. As we discussed on the meeting this week, there is some, we will talk a little bit about distribution, transformation, outliers, and coding, correlation, and that's it regarding, and that's it. So the data are, we can say, separated. I used all the time. So for example, you now show one notebook from EDE. I used, and that notebook used the simple original data sets. On the other side, I used the impute data set from the data engineering group. And in that data set, we can say that vehicle datasets can be separated in three groups. One is vehicle specific features, one is vehicle accident features, and then one is just information about accident specific features. And the original, and in the original dataset we have 24 features. On the in the imputed we have 39. A lot of them are objects, and we have just a couple of them that are numeric. Okay, here are distribution for these numeric ones. okay, because they are not obviously they are not show strongly Gaussian distribution, so I just create some information about them. And for example, I experiment for each of vehicle. I experiment with box Cox transformation, and what is interesting here. So it's interesting that it is interesting that it will show later on that this distribution is the same distribution as that we, for example, deleted outliers from these features, and it will be the same one. So that is observation that is interesting in, and also regarding feature. Okay, regarding outliers. Okay, here I calculated the number of rows which contain outliers, and outliers are defined 25% and 75 between 25 and outside of the 25-75, and so what is interesting here that, for example, okay, age of if we take firstly age of vehicle and then delete outliers, we can see that the distribution is the same as in the method with the box transformation, but on the other side, for engine capacity, that is not correct experiment, because we have a lot of in that way, if we remove outliers, then it will mean that we will remove a lot of vehicles that are higher than 3,000, which and they are like cars with higher are removed. So for these features, I said, okay, let's experiment some transformation, and log transformation. For I think that it's good because it also gives us, let's say, Gauss distribution, but on the other side, we keep all the data. We kept all cars with higher engine capacity. And okay, what else? Then regarding encoding, here are some attributes for the which are object in the data set, and then the standard one that also colleagues mentioned, label encoding. Firstly, perform some analysis on some of them, and then label encoding, and then for example, what is interesting that, for example, we have a lot of vehicle that doesn't have information about model. Exactly in the data set, it was written like missing, and I transformed them in the way that they are presenting information about the brand or make from the make column, let's say, because make is the brand. So that's it. Then it appears a lot of so because we here during the encoding we had we encode almost all of these variables. So it appears that we will have now more numerical attributes for further analysis. And here maybe one stuff that makes me a little bit surprise is regarding correlation matrix. Let's say that here I put correlation matrix just on this numerical feature that I encode in the previous step, and we are not reaching the highest correlation is just slightly more than 0.2, and we don't have some, let's say, medium or strong correlation between even all these informations are okay. A couple of them are from vehicle information, and couple of them are from accident. But also I expected correlations that will be a little bit higher. Here, as we can see, if we take a look at, for example, this one that are, for example, V, we can see that engine capacity, that V-car correlation between engine capacity, and on the other side, propulsion code, which is fuel. So, and we expect something like that because they are built like that, so that there is no weak that doesn't have that correlation between that type, that two types. But a little bit stronger correlation between model and vehicle type, and maybe that will be interesting for a little bit further research, further analyze. Also, I try to experiment a little bit with means between two attributes in this moment between age of band of driver and energy capacity and but this is and I use elbow method to find optimal number of clusters, but I'm sure that I need to do that we need more experiments with different kind of features, and I choose this one because in the notebook that you shared, they also analyze this relationship between these two features. So maybe a little bit, maybe you need to take a look at more at exploratory data analysis notebooks, and then use some of them, and that's it.
That's cool. That's good work. It's quite interesting that there isn't any sort of correlated features in the heat map, but I suppose the correlation it basically assumes that each feature is independent, and because it's just basically a description of the vehicles, I don't know. Yeah, I don't think it might be, you know, especially when we are using the vehicle data set to create a sort of analysis dashboard. I assume if we had a sort of predictive value within that data set, the correlations would speak to us differently. It's just that we don't, and so there's no real sort of storytelling of correlated features. It is quite an interesting one though. In terms of your last slide, and you use the elbow method, I think maybe using something like TSNE might help as well, if you're familiar with that. If not, I'll put some information in our Slack channel. It's basically used to sort of cluster high dimensional data, and I wonder what the vehicle analysis data would look like if you applied TSNE to it. It's an alternative to PCA, but obviously it can be used in a couple of, it is used for slightly different things, and it has different pros and cons compared to PCA. I'll share some implementation of that, and it'll be, you know, just an interesting experiment to see if it can make sense of our data, you know, the vehicle data set. But yeah, it's great work there, great presentations, some great insights as well. There's a couple of things in the chat. We've got you know, it's good insight that normal distributions, log transformation normalizes the skew distribution, and we should try taking square root and log anything to try to make the distribution more like a Gaussian distribution, which is very true. But you know, there's one thing I couldn't help but notice is that the age of the car is 7 years. It's just a massive value compared to everything else, and that is really interesting. And I've tried to figure out why that's the case, just by taking a look at, you know, other people's analysis of the same data set from the UK government, and I can't find much on it, to be honest with you. But yeah, that is a very interesting insight, and you know, it's very obvious when you've tried to, you know, in every sort of plot that you've provided, it just sticks out like a sore thumb. But yeah, thanks very much for that. That was very interesting, very well put together. I do like the presentation, color scheme on point, great stuff. Has anyone got any questions about that, or has anyone got any other insights that they'd like to share with the group? No? Okay. So yeah, I think the next stage is the model development. And I think we have a lot of information to go on. Let me just put my camera on, how rude of me. I think, you know, the next, you know, over the model development phase and deployment phase, we're gonna be going back to the feature engineering stage. It's gonna be a very iterative process. We're gonna be using things like PCA to reduce the dimensionality of our data set. We're going to, you know, use feature importance as well. We're going to be, oh, sorry, did I just see it in the chat there, Francesca? My chat's not loading. Hold on. Give me 1 second. It just crashed on me. Okay, here we go. Jawari had something. Jawaria? Is she back in the call? Yeah. Yeah, if you're unable to share it now, pop it in the Slack, Jawaria. If you're unable to share now, we'd like to take a look at what you've been putting together, please, because it sounded quite interesting. But yeah, as I was saying, it's going to be a very iterative process. There's going to be many sort of different techniques we're going to use in the data set, feature importance, PCA. We'll just have to, you know, using different sorts of classifiers like the passive aggressive classifier. I think that will help. Well, hopefully it'll help with the unbalance issue. We'll just have to run a few experiments and see how it performs, and you know, try a couple of different sorts of sampling techniques, maybe, or even isolate, you know, maybe, you know, see how a model performs by taking, say, maybe 10,000 lines of data for slight, serious, and fatal, and see if we can discern how a model performs when the classes are, you know, perfectly balanced, and then reverse engineer it to see if we can deal with the unbalanced unbalanced classes. That would be quite an interesting one to do as well. I think at this point, though, I'll be getting involved and getting stuck in and running a couple of experiments myself, just because I know there's a lot of, you know, there's a lot of beginners, and this is where it gets a little bit tricky to try and comprehend exactly how your model's performing, what features is it enjoying, what features it doesn't like. So yeah, I think I'll be running a few experiments myself. Always has done some great work as well. I think one of the most important things and important takeaways is that you can't really interpret your model if you don't plot your sort of training and loss and validation plots. They're very important to understand what's happening with your model. and its performance, whether it's overfitting, underfitting, and so on and so forth. You know, it is something that we need to do, and I think if we all try some experiments ourselves, we you know, we'll solve this problem together. But yeah, good work everyone so far. I'm impressed with, you know, again, impressed with the collaboration, impressed with everyone's effort. In terms of the time series, Akanksha, I think her name is. I'm terrible at pronouncing names. She's been working on the time series data set. I don't think they're here though, so no. So, you know, I'll catch up and hopefully get the you know, you can share the notebook to the drive. The time series analysis is quite technical. The data preparation is quite in depth as well. So I imagine that one will take the longest, but I will certainly be experimenting with that side of it as well, because I think it'll be really beneficial to our final solution of the dashboard. So yeah, I think at this point now, everyone starts experimenting with certain models. Let's just throw the data in and see what it spits out, and we can move from there. Dunia, you've raised your hand.
So, hi everyone. So please, Rich, I would like to know the alternative of PCA method.
The T-SNE method.
T?
It's, where is it? T-SNE. It's pronounced T-SNE, but it's T-S-N-E, and basically it's a method of dimensionality reduction. It is quite similar to PCA in terms of implementation, and it stands for T-distributed. Let me remember this: T-distributed stochastic neighbor embedding, and it basically it reduces dimensionalities, but what it does is group your sort of your features together. It's very good for high dimensional data. So it in a way it presents, you know, like your nearest neighbors algorithms and whatnot, where you can sort of plot your different groups and what features are similar to each other. It's sort of like that, and it's great for sort of trying to, you know, understand you know, what features are important to each other. It clusters them together, and to be honest, it's mostly done for its visual power. It gives a very sort of intuitive look over your data set. I'll put a few examples in there into the Slack channel in the knowledge sharing point. I've only used it a couple of times in the past, and I believe it's, you know, the medical industry use it quite a lot. I just don't work in there, but they use, you know, if you're dealing with sort of you know, DNA and you know, genomic data, it sort of helps to describe the families each sort of data point represents at a high level. But I'll share some information about that. It is quite interesting, and the output you produce from it, you know, it's really quite good, and it looks quite impressive, to be honest with you. But yeah, PCA is the usual go-to method. This is just an alternative solution for it. It does have its pros and cons, but as I say, I'll put more information in the Slack channel, and it'll be great if someone could implement it, just to give it a go. It might work, it might not. It might be useful, it might not. But we'll certainly check that. So yeah, it's T-SNE it's called, and I think someone might have put something in the Slack channel. I just heard it go. Oh no, it's the summary presentation. Thanks, Godana. But yeah, we'll take a look at that. I'll share some resources on it. Stochastic neighboring embedding. Yeah, that's right. But yeah, as I say, I haven't used it that much, to be honest with you. I haven't had the need to. It's just something that I have come across as an alternative to PCA. But you know, it's not a like for like alternative, as you know, as I've mentioned. There's pros and cons to both of them. you know, each one of them won't provide all the answers you need for sort of interpreting your model and see what is important in it and see how the features are related to one another. So yeah, I'll share a couple of links on that anyway, but thanks for asking. Any other questions at all? No? Okay, well, we'll leave that there then. Great work, everyone. We've done, you know, you've done an absolutely fantastic job. And I can't wait to see the sort of, you know, the techniques and experimentations we do with the modeling part of it. So everyone, please go away, have a nice evening, and we'll get cracking with the machine, with the modeling phase, and we'll check in on Wednesday. I will hopefully have a couple of experiments that I've put together myself, just using the data sets that you provided and the notebooks you've provided, and we can discuss our ideas, we can discuss our results, and as usual, we can come together as a team to make sure that we're moving in the right direction. But thanks very much, everyone. Have a wonderful afternoon, and I'll see you soon.
Thank you. Bye.